forward. Okay. Thank you. And for giving me permission. So sorry, I missed the beginning, but I didn't say anything important. Anyway. So we'll talk a little bit at the end, but the idea is also to put people in touch with each other and see if some future activities are useful or maybe they're not. And I think the reason why we haven't done this before, and we Kyle pushed us a little bit through this, is that people who write code worry that then they're going to get a lot of emails and have to do a lot of work that they don't have time for to support users. So the point is that we're giving you the code and people will try to answer emails, but nobody's promising extensive support. That's kind of the situation. And then, so today we'll go through that spreadsheet that Anne was showing earlier, which is here online, and you can find that the link. And then that has all the links if you want the code for most of them, and there are some YouTube videos for some pieces of code. So we'll go with that. And I think, again, thanks to Kyle for his persistence. This is just an image of that. So I think Kyle started with this.
So other Igor resources that are out there, Wave Metrics has a forum, Igor Exchange. It's a really good place to start. You can ask questions. There's an option for people to post projects. So for example, if you want a piece of code that will parse chemical formulas and tell you the number of elements and the number of each element, there's an example of that on the forums. You can also do feature requests to the Igor developers. It's a very healthy and helpful community. If you ask kind of a dumb question, which I have done several times, you don't get like, oh, that's a stupid question. People are really helpful and learn things. Wave Metrics employees are very active on this. I have talked with the person who wrote the function that I was trying to use that was giving me problems. And just as an example, there's a feature request that I asked them to do, and they're like, oh yeah, we can do that. And so they implemented it in the next version of Igor, which was nice. There's also an Igor mailing list. It's third party, but the Wave Metrics employees are active on this, and when they have a new version of Igor, they will send out an email to the email list saying, hey, new version of Igor. You can either get every email. What I do is get a daily digest just so my inbox isn't flooded. These discussions are usually a little more advanced than the stuff that's on the forums, but they're still pretty useful. There's a lot of good things you can learn just from kind of looking in on those discussions. So all of my code is available on that GitLab link. For most of it, there's a demo experiment that has some data and the relevant IPF adopted in the experiment, so you can see how things work. And if you need to contact me, my email is down there. So this is actually one where I would encourage people to reach out to me if there are issues. So iCart is unfortunately widely used in the atmospheric community for submitting data for campaigns. And the reason I say unfortunately is it's a very hard format to implement correctly. And it's kind of the bane of some of these campaigns where there's a bad iCart file and the person doesn't work there anymore, and so you can't get it fixed. We have this really nice GUI. Donna wrote the first version of it, and it's been updated ever since. It makes your life a lot easier, and it makes the lives of anyone who wants to use your data much easier because it handles a lot of the obnoxious formatting for you. Code is on Jose's wiki. There's a PDF README. There are help notebooks inside the IPF. If you have issues with this, or if there's things that aren't clear in the PDF README or just in how to use this, please reach out to us. We want people to use this. Like I said, it makes life so much better if iCart files are properly formatted. NASA is good about cracking down on people doing improperly formatted files. Other people are not. Other organizations are not. And it just makes life really difficult when the format is not correct. As part of the new standard for iCart 2.0, you have to include these things called standard names to improve usability, standardization, and machine readability. For example, if you have 3 in situ ozone measurements on a campaign, they would all have different variable names, but they would have the same standard name because in theory, they're measuring the same thing. The standard names document is a mess. It is document by committee. It's really hard to wade through. So we have this nice GUI where all the standard name stuff is in text files that gets read by the GUI. And instead of having to dig through this 100-page document, you can just use drop-down menus and things like the list box there. It's designed explicitly to handle updates to the standard name specification. There's actually a typo in the standard names documents about some aerosol outdoor property stuff. But if that changes, the Igor code does not have to change. There's just some text files that will have to get updated. And then hopefully this will be on the Jimenez group wiki as well. There are some quirks in this, but it works and I have other things to do. So I'm probably only going to do bug fixes unless the quirks really start to annoy people. Okay. So in terms of other more general stuff, so I just quick background, I worked for Maggie as a grad student. I knew nothing about programming and I've kind of progressed from just using Igor to make a pretty plot to writing code and workup data from an entire campaign. So I've kind of gone through the full gamut and made tons of mistakes along the way. So this little IPF prints the date and time when you save an experiment. It's really useful for keeping track of what you were doing when, especially if you go on vacation or go on a different campaign and trying to come back and figure out what you were doing. It's also really useful if you're trying to look at someone else's experiments and they've left the group and aren't in contact and you're trying to figure out exactly what they were doing. A shortcut to this lives in my Igor procedures folder. So it is enabled in every one of my Igor experiments, even ones that I haven't saved yet. And it's just a really useful thing to keep track of your progress. Also, for making figures, you really want to keep track of how you made the figure. I have been burned by this numerous times, both myself not doing this, and then again, trying to go back and reproduce a figure someone made in a paper, and they have an experiment and there's no documentation whatsoever. Two general ways to do this. First one, I stole from Jose's group. This is code that Carl wrote. It just puts a little text box on the graph that has the pass of the experiment, the name of the experiment, the date when you saved the image, and the graph name. I find that a little annoying because then in PowerPoint or Word, you have to either crop out that or put a white box over it or something. So what I do is I use a program called EXIF tool to modify the image metadata when I save it that stores that same information. It's a little bit harder to access the information, but you don't have to muck around with Word and PowerPoint. But whatever you choose to do, you really want to do something like this. It makes your life so much easier when you're trying to go back and figure out what you're doing.
So can I ask a question quick? So when you say you modify the image metadata using EXIF tool, so that means in the Word document, that image that you copied and pasted in there has that metadata in it?
Once it goes into Word, that metadata gets lost.
Okay.
And that's the drawback of this is you can't access it.
But it's in a PNG, I'm guessing.
Yeah, so it's a PNG.
Oh,
So
okay.
Igor makes a batch file that calls EXIF tool, stuffs that in the metadata, and then I have the folder of the drafts and the folder of the images, and I can
Gotcha.
go back and look at that.
Okay, thanks. That wasn't clear.
So also graphs, I have a collection of kind of simple graph utilities that are just useful to have. This is kind of a simple example. Two traces, one on the left axis, one on the right. I want the axis colors to match the trace colors, and I also want the colors in the legend to match the trace colors. When you change the trace colors, the trace symbol in the legend updates, but the text color doesn't, the axis color doesn't. And which is a little function that will go and update the axis colors to match the traces. It will update the colors in the legends to match the trace colors. This is kind of a simple example with only two traces, but if you have 20 traces on the graph, you don't want to have to go and change everyone manually. So just simple functions like this in this graph utilities IPF to do updates to graphs. For a lot of campaigns and projects I've been on, I found myself looking at the same plot, some concentration versus time, but for different experiments. So I have this data grapher function where you have a drop down of all the different events and you can set which traces you want to look at. And then you can just very quickly scroll through events and see like, oh, this flight, these two species are well correlated, but on the other flight, these two instruments didn't agree with each other.
Jason's true. I had a very similar tool, but we didn't know what to use.
So part of the reason for this is we really should stop reinventing the wheel and to tell people what's out there. And so I wrote the first version of this at NOAA because there wasn't one available. And I was like, someone must have done this, but I don't know who to talk to. So I'm just going to write my own.
That's the point.
I have better things to do. There's also a version of this that's still in beta, but it has a longitude plot. And the older version of this that I'm updating, I could drop a cursor on some interesting feature and then click the sync cursor button and it would put exactly where it was on the flight track. It was a flight we were going back and forth, and if you tried to drop a cursor on the flight track, you wouldn't always drop in the same place because it was just lines back and forth over each other. But with this thing, you could. But it's the same thing where you can scroll through events and you can look at how certain sets of data behave across different events very quickly. Also for flight data, it sometimes is useful to make KMLs that you can display in Google Earth. So I have this GUI. It takes inspiration from Ken Aiken's Igor tool as well as Dave Thompson's LabVIEW tool. But obviously, it's an Igor, has a lot of added features. You can make the KML line, or you can do markers, and then there's like the Igor F of Z, where you can color and size the markers by some other trace.
That's like a similar one that is my tool.
Yeah. Movie is not supposed to. He's not playing. That's unfortunate. So there's supposed to be a movie of a fire down here. Movies often are a really good way to show how data are behaving. So what you should be seeing is a fire, and you can see changes in the fire, whether it's getting stronger or weaker, and then those correlate with changes in those time traces of naphthalene and ammonia. The built-in Igor movie functions really do not work well. So instead what I do is I use Igor to make the frames, and then I use Igor to call a program called FFmpeg that will convert the frames into movies. FFmpeg is stupidly powerful. A lot of commercial video tools are actually built on it. And just as an example, you can have a gigabyte of image files, and FFmpeg will convert that into a movie that's only 10 or 20 megs, and the image quality will look great. There's a lot of other things you can do with it. You can change the speed of movies. So the Igor GUI that I have can do the speed change. You can remove audio from video, and you can also re-encode existing movies. So the movie of the fire that's supposed to be there was from a GoPro. It was something like a gigabyte. If you put it in a presentation, PowerPoint would crash. And I ran it through FFmpeg, re-encoded it, made the movie smaller, and now it's only like 10 megabytes. Really useful. It's free. Works on Macs and PCs. There's a huge community that uses it. There's a lot of information online you can get from it. Wave Metrics provides a code, an IPF for running multiple experiments in a row. So if you have some data processing you do on a bunch of experiments and you just want to click a button and walk away, you can do that. I do this a lot for campaign experiments where the analysis is at some point where I should do something that's standard, doesn't require me to be there. And there's also a set of scripts that I have that is this modified, it's modified from this multi-experiment, where you can have multiple instances of Igor open and you can run multiple sets of experiments in parallel. So I was processing data from a campaign, and I just had 7 instances of Igor open on a desktop computer, and I pressed go, came back in a week, and it was all done. Didn't require any intervention from me. It was great. And that's all I got.
Only 6 minutes behind.
As long as the slide number corresponds to the minute, we're fine.
Okay. So I'm going to talk about some code that's on my group's GitHub for doing generalized Kendrick analysis or mass defect plots. And just because a lot of people might not be aware of what generalized Kendrick analysis is, it's this formula up here. Where's the mouse on here? So up here. So in standard Kendrick analysis, R would be the IUPAC mass of CH2 and X would be 14. We let X be any integer, and then that expands or contracts your mass axis. And you can do fun things to improve visualization and ion assignment. So this would be your standard Kendrick mass defect plot. And this is a generalized Kendrick analysis one. The purple square, or yeah, I think the purple squares are the exact same ions in both plots. And then the circles are different ions, but there's the exact same number of points in each of these plots. And you can see how you have much better horizontal alignment with this new code. So this is all described in this paper down here, and the code's here. This is just a screenshot of the code and then the panel. So you go in, you choose your base. So like CH2, carbon, O16, whatever you want. You choose what your X value is going to be. You get different visualizations depending on what that integer is. You select your waves via drop-down menus, and then you can click this button here for calculate. Right now, what's up there only supports a 1D mass spec for the intensity, but the 2D one should be up next week. So then you can do a lot of fun things for changing what your graphs look like. So that's all in here. So you can choose color scales, you can size things by intensity, or you can color them by intensity, and you can choose your scaling, remove some number of largest points. So if you want to remove your reagent ions, you just say remove the 3 largest points, or 2, or however many you have. So just some percentage of signals. And then if you want to flip how you define your mass defect to be consistent with kind of the general mass spec community rather than the atmospheric mass spec community, you can do that here as well. So, and then over here, this is some really nice code here where what you can do is you can draw a polygon of your choosing, and it'll select this section of the code was written by Harold. It'll just select the points that are within that polygon, and then you can replot it however you want, changing either your base or your scaling factor, or keeping them the same, but just looking at a subset of your points there. So the plots that it creates a new plot each time you press the button. It gives a very meaningful name to the variables, and they're all saved here. So generalized Kendrick analysis with the base, and then what that integer was. You can see that here, and all the plots are labeled to make it easy to see. So, and this is one where I would, definitely I'm open to suggestions for improving this and what other tools you'd like to see, because we're working on expanding this, and particularly for making it useful for the SIMS community. So that was everything.
Hi, can you guys hear me okay?
Hi.
Great. I'm Lauren Garofalo. I'm a research scientist at Colorado State, and thanks for including the front range in this, because we have the same problem where our group is just rewriting the same code over and over again. So something that I thought was maybe unique for today was controlling LabJack within Igor. And so with Igor 8, it only works in 32-bit. There's some LabJack libraries for different versions of LabJack, and you have to install a driver. And so in a GitHub, I have a GUI for controlling like our RH and temperature probes, as well as a mass flow controller. And all the wiring instructions are in the procedure file header. It logs it, and so it has a Igor time, string time, voltages, and variables. And the timing is not very precise. It's about 1 second. It's mostly 1 second, but it's good for ground sort of stuff. We could go to the next slide. So this is what it looks like. And it's really simple. You can put in your offset and scaling for your device there in the orange box. I'll keep this really short, so go to the next slide. And then this is the mass flow controller panel. And so here you can actually use Igor to connect to multiple LabJacks and select between different active LabJacks, and then wire up to mass flow controllers to each LabJack. And you can again set all of your, set the range for your mass flow controller, and if you have a calibration and offset and slope, and you can scan mass flow control voltages if you want to just make sure that your mass flow controller works. And so this is available, and I hope that this community continues to meet so that we don't have to keep rewriting our own stuff. And this is also good accountability for us to get some of our stuff shareable and active in the community. Thanks.
Harold? Hi, everybody. Harold Stark, probably most people know me. I work for Jose's group and for Aerodyne. I do a lot of Igor programming. I actually get paid for Igor programming, so that might be a little unique. So I want to show two things that I've worked together with Jose's group here. The first is the photolysis calculator. So this is a little Igor tool that basically calculates photolysis rates, and is dear to my heart because I used to actually measure photolysis rates when I was working at NOAA. So what this thing does is you basically can give it chemical compounds and you can give it different light sources, and it will calculate the photolysis rates for those for you, which you see there on the middle graph. And then if you hit forward, nope, one back, please. It also has a component that is kind of fun. I don't know who of you knows that at NCAR there was or is a project to calculate photolysis rates just based on all kinds of conditions in the atmosphere, and it is web-based. So I was able to implement that into the photolysis calculator. So at a click of a button, that Run to UV button there will basically go to that web page that NCAR is maintaining and calculate the photolysis rates of the conditions that you input. And then it'll retrieve the data from there and makes the plot right there in Igor in front of you. So that was a fun project, and my favorite part of that is that fetch URL command that basically does send the command to the web server, and then it retrieves the results and turns that into these plots. So that was kind of fun to write, and it's a useful one if you have something in a web page that you want to put into Igor. On the next slide, I will go to my second project that I'm going to show here. This is the Gecko loader, also NCAR related, interestingly. So Gecko is a very large model that can calculate very complex chemical mechanisms, basically, and it gives gigantic outputs. And in a collaboration a little while ago, we were using well, I was writing this tool that would basically take these big text files, output files, and try to package them up into some graphs or tables and things like that. So what you see here is this front panel of that that shows you the output, basically all the different compounds you can get from it. And then when you click on one of those compounds, and if somebody could click the button for that, then you get the time series of these things that it outputs. And it actually partitions into gas, particle, and wall if you want it to be. It also gives you different isomers that are the possible products. And then if you want to know what the mechanism of that is, one more click, and then I think we're done here. It will also be able to spit out how this compound is either lost or produced from that mechanism with all the rate coefficients in there. So a nice way to really distill out the important information from this Gecko loader. And I believe I have one more slide. So I'm keeping this a little bit more Igor-centric than two. The most challenging part was reading and parsing these text files in Igor, but I did work it out. So that could be a helpful one at some point to see. And then the most fun part is these automatically updating panels, which you don't see because it slides. In a live demo, you would have seen as soon as you click something, something else updates, and that uses these named window hook functions that I wanted to mention that are really important for that. I believe that is all I have to say here. And yes, we should have another one. Sorry, I'm not there in person. Would have loved to hang out afterwards to discuss more things, maybe in a quieter or more relaxed atmosphere. Thank you.
Hi, hi everyone. I'm Zhe, working with Jose. This is a software, a kinetic chemical kinetic solver. I've been working on since I joined the group. I took over the code from Harold, and I believe he took over the code from Jim Burkholder. Yeah, I put the information here on the panel. Kinsim is an very easy to use kinetic solver. It's visual, interactive. It has a GUI here. And basically, if you want to do a chemical kinetic simulation, you just need to click the buttons on the panel in order, and fill the information in different tables that pop up. For example, here, if you click step 1, and then the table for step 2 popped up, and you need to enter the mechanism information, reactants, products, and the rate coefficients. Then you compile the mechanism, and then you need to enter the initial concentrations of species. Then click this, step 3, then you need to enter the scaling factor wave for some quantities that varies with time. For example, UV intensity. This is for step 4, and then you click step 5. The model runs, and you get the output almost instantly if you don't have a huge model. There you have concentrations over time. And then if you want to, you can click step 6 to get the reactive flux balance for certain species. We've already built a Kinsim user community of a certain size. Now it has almost 300 registered users, and there are already 43 published peer-reviewed papers using Kinsim. And I want to mention a big advantage of Kinsim is it can easily export the mechanism, the whole thing, into an ITX file, and then later others can just load it by one click, and then your model is directly ready to run. I think Jose is going to discuss this functionality more, and some available cases for demonstration later.
Oh, okay. So you're
This is another series of tools I've developed along with Jose, and one tool for by Brad Prom and Jose. All these tools are for oxidation flow reactors. They're basically for designing and interpreting OFR experiments. This is the OFR exposure estimator. With this tool, this is based on the estimation equations fitted from my modeling results for OFR chemistry. We have published a series of papers containing a bunch of estimation equations for different key species in OFR chemistry. With this tool, if we enter the experimental conditions on the panel and hit this button, we can get exposures or concentrations of key species, and some key diagnostics to analyze if this condition can produce results of atmospheric relevance or not. And again, this is based on estimation equations fitted from modeling results. If we want to directly model that the OFR chemistry, you can use Kinsim, and we have a directly loadable case for OFR chemistry. Next slide, please. And this is the some key outputs of the OFR exposure estimator. Concentrations or exposures of some key species, and some key exposure ratios, and some fate of VOC under this condition. And this is a graph basically reproducing the information of the colored outputs in the table. And it's and the right plot, colored plot, is to tell you if the your experimental condition is safe, risky, or in a transition regime in terms of atmospheric relevance. Please move on to the next slide. And we can also use the OFR exposure estimator to estimate R2 fate has R2 fates. This R2 fate estimator for OFR is a part of OFR exposure estimator. We just need to enter the rate constants of different R2 loss pathways, and R2 reactant concentrations are fed by the exposure estimator once we enter the experimental conditions. And then if we click this button, we get the pie chart of the R2 fate. And next slide, please. We have another version of R2 estimator, which is for more general use. This estimator is no longer part of OFR exposure estimator. So the input species concentrations are not controlled by the exposure estimator. We can enter it ourselves. So we have more input options than the OFR R2 fate estimator. But it's still quite similar to the previous one. And after we hit this button, we can get pie chart of R2 fate. Next slide, please. And this is another tool for OFR experiment design analysis. It's for LVOC in OFR. Because LVOC in OFR can have different fate, condense onto particles, react with OH many times, or lost to the wall or exit to the wall, because OFR residence time is relatively short. And this tool, I don't think it has a panel, because it's developed by Brad Palm and Jose. I just describe it here. I don't think it has a panel, so I showed its code. We need to feed the model with a wave of condensation, waves of condensation sink and photochemical age, and a number for residence time, and we can run it. And then, yeah, these waves can be from field measurements or lab studies. So, you know, it's observations, not model, which are usually quite smooth. After we run the model, we can get fractions of different LVOC loss pathways as a function of photochemical age. And that's it. Thank you.
The order was changed, so I was came after Kinsim. So this is just some cases for Kinsim. So Jeff has done 99% of the programming since we took Kinsim over. Something I've been trying to push is this idea that you can quickly load cases, and those of you who have taken courses, we've done some of that. And there is cases like very simple case for stratospheric ozone, tropospheric ozone, nighttime chemistry. You can build on those for research applications. I wanted to highlight one that I think is the one we end up going to most, which is SOA formation with wall losses. These are away for now. Which is that scheme over there in which you have species that can partition to the walls but can come back, and other species can partition to the walls, and they are lost irreversibly, and then they can also partition to the aerosol. And this took me quite a bit and 20 conversations with Paul Seaman until I understood how to model it. So we save you all the pain, and basically you have all the numbers and you have an explanation, and then you can run your case and see what happens to each one of your species. And then if you have a mechanism that's more complicated, it's very easy to modify. You can just change the vapor pressures, add more species, but it's just all the same repetition. So anyway, I think this is one we end up building up a lot. And then what we've been trying to do is when people write papers to ask them, okay, can you, so you have your paper finished, and then you go to Kinsim and say, save a case. And then it saves a file. You send it to us with some explanation, and we put it there, and other people can build on your case for a future paper. So we have a bunch. I mean, all those OFR cases that Jay mentioned have 100 reactions. There's also one in which you have one reactor, and the output of that goes into another reactor. You can also play games or have different components. There's cases for IPOX, terpene, VOX. I mean, things that we have done in my group. I think most of the cases are from us. We have an indoor chemistry case that we're working on, and we'll put it in there when it's a little more mature. But I wanted to ask that if people use Kinsim in a paper, to please remember to, after the paper is in press, basically to send it to us, and then it's there and can help other people again, not to reinvent the wheel. You can always, I mean, it can always be very confusing, try to read from a paper and you have a number that's wrong and then it doesn't work. And you can see. And this is the link where you can find the information. Melissa.
Hey everyone, I'll try and keep this really brief. So I'm the caretaker / developer of our two models to simulate gas sorption in polymer tubes. So today I just wanted to briefly go through the use cases for both of these tubing models. So the first one has been around for a while, so maybe you've seen presentations on it, but it's a single layer model. So the use case for this one would be if you have an experimental setup in the lab or in the field where you have, for example, some length of PFA tubing that connects your instrument to whatever you're sampling, whether that be a chamber or going outside. You can input your experimental parameters into this model and have it tell you which gas volatility bins you are transmitting perfectly, which ones you're transmitting with some kind of time delay, and which gas volatilities you're not going to see at all through that tubing. So this can be really helpful for quantifying what you're losing in your inlet. And then the next one is the multi-layer model, which I kind of built from Luke Algrim's model for paint sorption, and paint is highly, highly sorptive. And so I used this to characterize some really highly sorptive tubing materials. And so this has a little bit of a different use case. Basically, after characterizing those materials, we can use them for pretty crude chromatography. So the use case for this would be if you're interested in separating a sample or ambient air or something into different volatility gas bins. You could use this model to try and figure out what kind of tubing and what kind of lengths would provide you with the separation that you're interested in. That one does not have a pretty panel, but if you're interested in using it, or if you're interested in doing gas phase separation with inexpensive tubing, definitely shoot me an email and I'd be happy to have a conversation. And then I wanted to give a shout out to our favorites since we've tested a lot of different tubing materials. Just a reminder, we have our reigning queen, which is PFA tubing. If you want to transmit as much as possible, that's the best one to use. If you want to denude as much as possible, you should use the black TSI conductive silicone tubing. Just as an example, if you flowed the same compound through each of these tubes, In 20 minutes, it would go into 10 nanometers of the wall of PFA, and it would go 300 microns into the conductive silicone tubing, and you're not getting it back. So that's why I use the black hole emoji for that one. In cases where you're interested in gas and particle sampling, not just gas sampling, we continue to recommend aluminum foil wrapped conductive PFA, which is different than the regular PFA. Or if you absolutely need a metal tube, then we recommend a silanite coated aluminum.
Hello, my name is Pedro Campuzano. I've been working in process group for a number of years. I was going to present here two packages, one that I sort of inherited and another one we are actually still working on and could use some testers at some point. So the first one is basically a simple calculator for me-scattering. So basically you want to interpret the output of a nephelometer, compare it with a sizing instrument or aerosol mass spectrometer. The original code is basically from a textbook, and Chuck Brock basically ported it to Igor in the early 2000s. That code basically got passed on to our group, and some wrapping fractions were written, and I cleaned those up at some point, and I've been basically maintaining since. There's a very similar code, I think, that Chuck Brock's group has at DOA. And I also want to point out, since this is really not that user-friendly. So if you want something with a panel, there's this thing that Roya Varani's student built, which has buttons and all those things. And that can also be used, and it's based on the same code base. What this code is good at is you basically have three functions. One gives you the scattering for one particular Morris-Burrs particle. The second one gives you for one size distribution, and the third one gives you for many size distributions. So it's perfect to plug into your own code and run it through for loops and whatever. So that's really the strength of this particular package. And it's been publicly available since 2016. So and I'm happy to answer any questions. So on that. And these are just some examples. So on the left side, you see basically what we have been using it for to compare basically the output from a particle sizer with the actual measured scattering, and try to see if you can get closure with reasonable refractive indices or not. And the other one is an example where you can actually use it more for a diagnostic of how do optical particle sizers work, what is the response function. And if you want to know more about that, there's this paper from Moore 2021 that actually used the NOAA code that's very similar to this one to actually simulate these curves. So, okay, the second thing is Amati. This is a thermodynamic model front panel that we've been working. Well, I started this like about 10 years ago, and yeah. So the important thing about this is this. I think somewhere in Boulder, several groups in Boulder have an executable of this EM thermodynamic model that is validated. This particular implementation has a DLL that is like 1,000 times faster, and that allows you to do a lot of things that you couldn't really do with the old system. And anyway, it's supposed to be an easy to use, especially for field people, way to calculate liquid water content, pH, and other thermodynamic things. And since it's fast, you can also, so this is basically the main products, and some collaborators are already using that. So, at the bottom, you can see estimated liquid water from the thermodynamic model and also from OA with a simple parameterization. And on top, you can see pH, different types of pH, and, masked by different criteria that basically, are supposed to give the non-expert user a sense, can I really trust that pH in that region or not. And last, as I said, since the model is much faster, you can do a lot of games. Like, if you're missing one input, you can just iterate on that input till you get a consistent answer. That's basically what the left thing is showing you. So you run this like 500 times, and at some point, you actually get the measured and the modeled nitrate to converge. And then you can use this, the same procedure to also estimate, how much the measurement uncertainties actually impact the pH in different conditions. And yeah, this code we are planning to publicly release it between October and Christmas. And if anybody wants to be alpha tester, shoot me an email.
So recently one dog is on vacation in Hawaii, 10 miles from where the fires were yesterday. So he wasn't able to participate. And he's recorded a 5-minute video where he goes button by button, but I thought that would be too much detail because that's basically what you would do if you actually want to use it. And I encourage people to do this. You record yourself in Zoom as you do think around in the screen, and then you put it in YouTube. It's very easy and it's very useful. I've done that also for KinSim for the class, and I think people also think it's easy. You can go back and see what's going on. Anyway, so what this code does, the idea is that you can load this MPS data. It works for TSI, and we're updating it for a new format. But basically, you can load anything. You would just need to mess with the functions, the loading functions. But once the data is all in the same format, and then it basically does the plots that you will want to do. I mean, you see all those buttons there. But basically, you can get image plots or time series of number, surface area, condensational sink, or volume. And you can also get size distributions at different times, and that kind of thing. So it makes doing this easy and exploring the data. The condensational sink is one that's very important, like for chamber experiments, whatever. It's always really confusing because the formulas are really strange. So this saves you. People have checked that this is the right formula, and you can use it that way. And a number of people have asked for this code. There's maybe 5 or 10 users around the world, so it seems to work well. No.
Hi, everybody. Most people know this part already, but many years ago, Ingrid Ulbrich and Jose's group created a panel for interfacing with positive matrix factorization, or PMF. I inherited it, and I am kind of the keeper of it with a little bit of help from Harold. It was created for the usage of AMS data, but it can be applicable to any other 2D data. So I'm just showing a quick picture of the first part of the panel. There's 2 main buttons, one where you prepare the data, the other where you say go, and then it often will take a very long time. So some of these data prep steps may not be applicable to your data. It deals with minimum error, NANS, weak signals, and possibly duplicated signals. And then there's 2 sections here that were initially put in there for quadrupole AMS data, which most people will never have to think about or use. Most people spend a lot of their time on this monster panel, which shows all the graphs that can help you come up with a solution. If you've ever done PMF, the question always comes up, what is the correct solution? And so here you have at your fingertips, lots of different graphs to look at to help evaluate and come to your own conclusion about that. Then the other tool that I want to talk about is something called general macros. When I left NOAA, I think it was in 2006, Goodbye Present was for me to gather up a lot of functions that I thought were being used in the Chemical Sciences Division lab where I was at the time. And when I said goodbye, I said, here you go. And I told Ken Aiken kind of became the keeper of that. And so he kind of is the official keeper of it, but he and I talk every time that we want to make any changes to this code. So that's where right now it's accessible in those 2 places. Initially, the ARCART code required the use of one of these general macros, but Kyle doctored it up so that it doesn't need it, so that would be helpful. The code was written a long time ago, and sometimes when I look at parts of those code, I just kind of cringe a little bit because I would not do things that way anymore. However, I think the value here for this community is that this code might be a good kind of entry ramp for people just beginning and not really, even maybe intimidated by a for loop or something like that. A lot of the code is real simple, 15, 20 lines. And it might be a good place for brand new users to get some coding techniques. Some example of functions in this graph are averaging functions, especially if you're dealing with some other instrument that has a different averaging period. It's always can be a little bit daunting, especially to new users, as to how you're going to like line things up in time. So there's a whole different way, you know, just a whole series of ways to kind of get your data on the same time base by averaging. There's some functions regarding wind, because you need to average wind carefully. You just can't average the wind, because it kind of actually goes around the circle. And there are some functions that help you with displaying wind barbs. There's things for dating time. And again, these last two items again are for kind of the beginning Igor programmer. Examples of how to use this $ syntax, which often confuses new users. Using lists to cycle through a whole series of waves, or, you know, other objects that you might need to iterate over. And then some other numerical functions like find first greater than or equal to, like you have a wave and I want to find where the signal went greater than 1 or 2. These kinds of functions are there for you. They're whatever, 15 lines long, very simple. And also another important one is interpolating across time. You don't have for whatever reason, you don't have a point, or you have a NaN value in one point, and you have a way to just kind of interpolate a line and guess what that value would be where it's missing.
Oh, it's me again. I want to point out that the link that Donna had and the ones that I'm showing here are all wrong, because I had to change them all this week. So we'll update the presentation and that will be correct. But, you know, just as a heads up. And I should say what I'm going to show you now is more like what Kyle was showing. So it's not so much atmospheric, but just general functions, and just a bunch. I know we're almost at the end of time, so I don't want to overstretch it here. So one is actually from Jason Schroeder that I'm basically been maintaining since, and the other ones are two things that I use a lot. So the first one is Jason's multi-tool plot. I mean, I think everybody in this room has some experience with that. So if you're trying to make a nice, you know, multi-panel plot for a paper, you can either make a layout, which is kind of awkward, or you have to basically go manually and build up your, you know, multi-panel plot, and that is very painful. And what this function does is basically it makes an automated layout for you that then, you know, you can then refine. I mean, it's really just as a setup, and as you will see, it saves you a lot of time. So on the left side is basically, you know, something I would normally make. So you can, you know, let's just say you can set up in what type of, you know, if you wanted 2x5 or 5x2, or, you know, this size or that size, that coloring, that. So that's all possibilities. The right one is, I really made this just for this presentation, just to show you what you could do. So this is 49, you know, different species from the toga instrument versus EO. And it took me literally like 4 minutes to make this. You know, I didn't post so much, but, you know, so you probably wouldn't do something like this big for a paper, but probably a 30 panel I've seen. And, you know, being able to do this quickly is, you know, useful. So, and I think actually even some of our group members are not aware that we have this. So that's, anyhow. Then the second thing is basically a general histogram tool. I should say this is a lot of things. Most of this didn't exist at all with Igor 6. I think Igor 9 actually has some of this functionality, but, you know, since then I've added a lot more. So this is just a, you know, what we basically do all the time in atmospheric chemistry, that we're trying to basically segment data by bins of one particular master variable. And as I'm showing here on the left side, you know, that what you do typically is either you do equal spacing or you do equal number of points, if you're depending on, you know, what you're trying to be interested in. So that's your master wave. In this case, that would be altitude. Just going to show mostly aircraft data, and then, you know, and then you can basically take a second wave and do basic statistics on that based on those bins. And my function will basically give you average but standard error, standard deviation, or if you want median and 25-75%. So that's all basically. And the important thing is you can do this on thousands of waves in one command, not just in one. So importantly, you can do this also for the 2D case. So up there is a plot that I will get back to. That's basically all the size distributions from the NOAA instrument during ATOM2. A month of data, and superimposes basically the altitude as we were flying. And then basically the bottom is if you now essentially make 12 bins in altitude and just calculate the average size distribution for each altitude. Again, one command. Third thing you can do is if you have set up your bins, you can, instead of doing averages, you can just really have it give you waves that have just the data for one particular bin, and then use that. That's basically what is shown here. So you would split the data into 6 bins, and then you can do your regressions or other things there. The left side. And then the right side is fairly complicated. As I didn't actually mention that there's this Google Doc that actually has most of this. So if you want to read more on that, but this is essentially an idea that you're basically doing the covariance of 2 variables, but as a histogram. So you could do this the same way as a scatter plot, but especially if you have a lot of data as a histogram, you might be able to see trends better, and you can also look both at the number of points or at the averages. And especially for exploratory things, this is fairly useful. Okay, that was the binning. And then the last tool I wanted to show, which again, is very much what I need to use all the time, but I think any type of synthesis work that you guys are doing, where you're trying to get many campaigns together, whatever, this is fairly useful. So we start with a folder on your hard drive with a lot of experiments. And those experiments are hopefully structured similarly and have the same waves in the same place. And it doesn't have to be waves, it can be S bars and N bars as well as you want. Right? And then say, this is now just an example for one of these experiments. I have these 3 different things. So a 2D matrix, 1D wave, and another type of 1D wave. And so with one command, I can go and basically combine all of these into one. So basically just loads them and concatenates them, which is gives you basically that ATOM2 overview plot that you saw. Obviously in big missions there are merges, but this way you can do it yourself. What is important is that this code is also able. So I picked that particular variable because I knew that these guys had one flight where they screwed up and didn't have data. But the thing is that the code will know that the length of the wave has to be a certain length. They will just pad them with nuns when there's actually missing data, so that everything always aligns. And the third thing you can do, and that's why I have this, is that you can also, instead of concatenate them in this direction, you can just make a 2D image. And then, so this way here, this is basically just the peak shape of the EMS for one flight. And here, basically, I put them all 12 of them, and can plot them basically as a wave plot, as a waterfall plot. So, and that's all I had.
And miraculously, we're on time.
Shockingly.
Shockingly. Thanks everyone for staying on time. So anyway, this was an experiment. So the question to be discussed now or later is, what do we do? Do we do this just again next year in the summer, or do we do it more frequently, or do we do some other kind of event? Focus on one tool or meeting with coffee, or as I was discussing with Melissa, it seems that pizza is the strongest force in the universe, and maybe we could use it to get people in the room. Or, we can create an email list or something, whatever, but then, we all have a lot of distractions. So I don't know. Also, something that occurred to me is maybe some kind of mentoring system that maybe one experienced programmer has a mentee or something like that. Anyway, everything takes time, but I just wanted to, it sounds like there will be ways maybe to do some of these that wouldn't be very time consuming and would be useful. So I don't know if people want to comment on anything or have any suggestions now, either the people here, I think we have 15, and there were 20 people online a moment ago. I was checking, so I don't know if anyone wants to comment.
So my original idea when I brought this up with today was to have a Google Doc or a wiki, and there would be someone who would be in charge of that, and people would say, hey, I have some code I want to share. Here's a brief description, and here's the link to the GitHub repository. And then it would just be there, very clear that this is as is. But then when people are out there looking for stuff, they can go, like, oh, I have this, because I've rated Jose's wiki for code before, but there were a lot of other things that, yeah, I just couldn't find, and I wanted an efficient way to distribute the tools that I developed that I think are useful to other people. So, and that to me seems very low energy for people. So it's just link and.
So like some just keep expanding here, or keep another tab for more things, or some organized version of this.
Yeah.
Okay.
And again, have one or some subset of people who are the editors of it, and then if someone wants to add, they just email, whether comments, things like that.
Thank you. Other comments or questions?
I thought it was really helpful, just because some of these things are tools. I was like writing down, oh, I can use that. Oh, I can use that. And I didn't know half these existed. And I think I like this format of like a quick and dirty, this is what's out there, because I think sometimes, especially as I know as a new grad student, like Donna, some of you are like learn what is a $sign, how do you use that? I think that'd be really helpful for new grad students. It took me a long time to figure that out, and I liked this format.
Yeah, I guess like during the earlier days orientation or something, like we can say like, here's a list of resources and feel free to like check it out. Just know where to look. Tab.
So, I mean, it sounds, I don't know if people online have any comments. I mean, it sounds like maybe we'll try to do some more organized version of this list, as well as maybe by default we'll maybe try to do this again next year, and then probably we will have to go through so many things because it won't be the first time. And anyway, and the most important, people know each other and whatever. I have learned about software my group has had, and I had no idea, and I want to use it now. So this is, I definitely find it useful. And the last thing, Donna is friends with the other people, and they send us some goodies. So they send us some.
Yeah, they're just buttons, little Igor buttons.
So everybody who presented this about now we have 2 hats and 1 cup, and I don't know. I think Kyle deserves whichever of the 3 he wants.
I've got a button, I'm good.
Yeah, but otherwise, I don't know if people we didn't get around to have a form or something to vote, but otherwise. I think I'll volunteer our youngest presenter. I'm interested in the
I would take a coffee cup.
Okay, so Lisa has won a coffee cup.
Thank you. She won't drink coffee.
And,
I kind of think Kyle needs a hat.
Yeah. You like the dark hat or the red hat?
Dark hat.
Good choice, Kyle.
Okay, so I don't know if anyone wants the other hat, otherwise we save it for next Igor.
I have a hat collection, but I didn't present, so we should save it. That's right. I gotta spruce up my code now. I'm gonna be sharing what it is now.
Well, thanks everyone, and thanks everyone online for participating. And, yep.
Yeah,
Have a
thanks
good
for
day.
opening it up to other folks too. I really appreciate that.
Oh yeah, thanks for contributing.
Thank you. Bye.
Let's see.
So one of the